All right, good morning, everyone. I'd like to take the opportunity to welcome you to the ARMA Induced Seismicity Technical Committee's monthly webinar series. So on behalf of myself, Sean Maxwell, Ahmad Ghassami, the committee chair, Jens Sneed and Madi Haddad, we welcome you to the webinars. Next slide, please, Madi. So this morning, we're very excited to host Sherilyn Williams Stroud with the Illinois State Geological Survey. So Sherilyn will be talking about the CO2 monitoring that's been taking place over the last several years at Decatur, Illinois, a really interesting case study. So just before we get to that, though, just a couple introductory remarks, and I'll pass it over to Ahmad to say a few things about ARMA.
Thanks very much. Next slide, please. Yes, for those of you who are not familiar with ARMA, I'd like to share with you a couple of slides and share some information that might be useful in the near future. First and foremost, we will have our annual ARMA Symposium in Santa Fe from June 26th to 29th. And in conjunction with that, we are planning on an induced seismicity workshop. Likely will be held on the 25th of June, the Saturday before the start of the symposium. And so if you have ideas that you would like to share and present to an interested audience, please consider attending that workshop, and we will provide more information on that shortly. Next, please. And again, ARMA is a professional society that serves all people who are interested in rock mechanics and deal with subsurface development of resources and construction, from mining to petroleum engineering to geological and civil and other areas of subsurface activity. If you're not a member, we encourage you to join. It has many benefits and it's really cheap, $100 for an individual membership. Students can join for $25. And if you don't want to deal with writing checks every 12 months or so, just become a lifetime member and pay $1,000 up front and you're set. Next, please. And if you have a company or are a member of a company, you would consider probably joining as a corporate member. There are different categories of this membership, from bronze to gold, and you see the prices there. And for this, you will get recognized every time at the annual symposium, and we'll have access to a booth. You get a discount on that, and we'll have access to the trade show. And there will be some discounts on individual membership as well. And for more information on that, you can contact Peter Smealy, the executive director. All of these different informations pertaining to ARMA can be found at www.armarocks.org. So please go ahead and explore that if you haven't done so already. And I would like to also express my appreciation to our speaker today, Sherilyn. And it's great to see you and looking forward to your presentation.
Okay, well, today we're hearing from Sherilyn Williams Stroud at Illinois State Geological Survey. And in the upcoming 2 months, we also have a couple of really interesting speakers, Sergei Shapiro from Free University Berlin and Jim Dietrich from UC Riverside, formerly the USGS. And the two of them, as many know, have some of the key models for earthquake triggering. And so it'll be really quite interesting to hear from them back to back. And we continue to add new speakers. Note that it's usually the first Friday of every month at 10 a.m. US Canada Central Time. For Jim Dietrich's talk in January, we are actually aiming for the second Friday of that month.
Good morning, everyone. This is Mahdi Haddad from the Bureau of Economic Geology. First of all, I would like to thank all of you who were able to join us for this webinar. We have a diverse group of academic, industry, and regulatory agency people in this webinar series. We would like to expand this community, so please feel free to share this webinar invite that you receive in the form of email with your colleagues and interested parties. If they want to be added to the distribution list, please let us know about that. So for better flow of this webinar series, we would like everyone to be muted during the talk. If you have any questions, please feel free to type that question in the chat function of the Zoom meeting. And please submit these questions to all people in order for us to summarize the repetitive questions, and in order for us to know what questions you would like to ask. We have this mindset about this question list before moving to the question and answer segment of the meeting. And this specific Zoom meeting is being recorded and it will be uploaded in our YouTube channel. Please refer to the chat function for the link to this YouTube channel. I typed it right at the beginning of this meeting. And without further delay, let's invite Sherilyn to start the talk. And I look forward to that. Thank you so much, Sherilyn, for this talk in advance.
Thank you. I just need to find my presentation again. Sorry. Okay, there we go. All right, how's that look?
It's good.
Okay, great. Thank you for inviting me to give a talk in this seminar. I just want to say I'm a structural geologist. I'm not a seismologist, but I guess I fit the many of the categories for ARMA membership. I've been a member of ARMA for more than 10 years now, probably 15 years. And it's my favorite organization because I like the diversity, and I like the size, and I like the subject matter. So whenever I go to an ARMA meeting, I find a little bit of something in all kinds of categories to learn from. So thank you for inviting me to present today. So what I'm going to talk about is the Illinois Basin Decatur project and the other project we have going on in Decatur, which is the Illinois Carbon Industrial CCS project. And I think a lot of people don't know that there are actually two projects there. The first one, which I'll call the IBDP project through most of this talk for short, was a large-scale demonstration project where 1 million tons of CO2, supercritical CO2, was injected over a period of 3 years. That project has ended. We completed it in June 2021 and delivered all of the data that was part of our expectation from the DOE contract to DOE, and they're in the process of making it publicly available. The Illinois Industrial CCS project, which I'll call ILCCS or ICCS, is an industrial scale demonstration project going. So supercritical CO2 is being injected still, and the injection rate is significantly higher. The idea was to inject 3,000 tons per day. It's not quite that much, but it's my understanding that ADM, Archer Daniels Midland, the corporate partner there, is injecting all of the CO2 that they are producing. So that makes it commercial at this point. Well, a commercial scale project at this point. And to date, there's been more than 3 million tons of CO2 injected if you include both wells. All right, to give you a setting for the geological context here, the states where you can see the geologic contours are, what I'm showing there is the top of the Precambrian basement. And that green outline is the outline of the Illinois Basin. The little black square that you see there just below the Illinois, now there's a red star, is the location of the Decatur projects. And here's a stratigraphic column. And the Mount Simon sandstone is a brine reservoir. At the bottom, it sits nearly on top of basement. There's another unit just below it, that's in between it and the basement, that it turns out to be fairly important in terms of induced seismicity. And the blue labeled units are the seals. So the primary seal, sorry, I said that backwards. The white labeled units are the seals. The blue labeled units are reservoirs like the Mount Simon, or potential reservoirs that could hold CO2, and some of them actually have oil and gas. So the Eau Claire shale is the primary seal, which is above the Mount Simon sandstone. And then there's two other regional seals, the Maquoketa Shale and the New Albany Shale. This is an air photo of the site, or near the site, and where the wells are. And you can see right here is the CCS1 well, the red dot here. That's the first injection well. And the second injection well, CCS2, is up here. And I'm showing you this cross section here through the wells, because I'm going to show you the well logs for these, and cross section through these with the stratigraphy, and what we learned, how the pressure progressed relative to these wells in the stratigraphy later on. It's not coming up next, but it'll be later on. So keep that cross section in mind. So there's a lot of data, seismic data available. So what I'm going to focus on is what we learned from analyzing the active and passive seismic data. So this slide is showing the acquisitions for the active seismic data. So the next slide I'll show you will show there's two long seismic profiles and 4 high resolution 2D profiles. Those were taken before injection, acquired before injection started. And then also before injection started, vertical seismic profile, and 4 monitor surveys later on after injection. And then there's also prior to injection, a 3D high resolution seismic survey. And it says January 20 and 21 because basically we realized we needed more extent to the north. So the 2010, 2011 surveys are actually together comprise the baseline survey. And then in 2015, after injection stopped, a high resolution 3D seismic survey was done. And we did a lot of the first interpretation was done on that. And that was after the induced seismicity was detected. And so we knew that there were faults there, but we couldn't see the faults in that seismic data. So we went back in 2019, reprocessed the 2015 3D survey to see if we can get better resolution of the faults. So this is the events. So you can see what the geometry of the events looks like. They're in clusters. It's on top of a hill shaded and LiDAR image. There, you can see all of the surveys and all the acquisition, all of the acquisitions that we did there. So the 3D seismic survey is that grid. The blue, the cyan squares are locations of USGS seismometers. So USGS installed a network of seismometers around the site to detect induced seismicity. The red triangles, this one's also supposed to be red, are the ISGS seismometers. So we also had 5 seismometers around the site. You can see, if you can see these sort of purplish lines here, these are some of the 2D seismic lines that go through this. So the 3D survey, as you can see, doesn't cover all of the induced seismicity, but we did cover areas where we have induced seismicity, and hopefully could go back in and see if, once you interpret the faults, if they had anything to do with the induced seismicity, because the desire is to be able to identify faults that could produce concerning seismicity before you inject, so you can design your program so that you don't reactivate those. And let's put it in the context of the historic natural seismicity in the Illinois Basin. This is the catalog only with earthquakes that happened in Illinois. Of course, you know, there are a lot more than that. This NMSZ down here is the sort of the location of the New Madrid seismic zone. So of course, natural seismicity increases down in this area. But what I wanted to show you here is that there are a number of earthquakes, natural earthquakes in Illinois that are detected by regular sparse arrays that are installed by USGS, for instance. And when you look at the source mechanisms of some of the larger earthquakes, you see a strike slip failure, and that's consistent with the maximum horizontal stress azimuth, which is pretty much 68 degrees for most of this area. That's what we've measured in the Illinois Basin area. So the dot there is the IBDP site, and then you can see two of those long seismic lines going across there. And so if you look at a radius of about 100 kilometers around the site, you can see that the Illinois Basin Decatur site is in a lower seismicity, natural seismicity area. And these, what I'm showing here are earthquakes in Illinois since 1795. And our engineering geologist who's been, you know, sort of keeping track of and building a catalog of the earthquakes and the stress in Illinois, went into, some of these earthquakes were happened obviously before these more modern networks were installed. And he went into newspaper articles for small towns to find out who felt it and how they felt it, to make sure that the earthquakes were located based on that. So we think we have a pretty good set of historical earthquake locations in Illinois. All right, and those I just highlighted as the largest earthquakes near the Illinois Basin site historically. These are all fairly old earthquakes, and the largest one, I believe, was magnitude 2.7 within that radius. Okay, now you can see why we reprocessed the seismic, how difficult it was to try to interpret faults from that. So the top rectangle here is showing the first process vintage of seismic. I like to look at seismic data with no vertical exaggeration. And I've projected 3 of the wells onto this section. And the bottom is the reprocessed seismic. And as you can see, now you can see things that look like you might be able to interpret them as faults. And I didn't do the interpretation. I'm not that, I guess the word would say, the word to describe it would be maybe, I don't want to say not confident, but I think you have to feel, know more about the seismic attributes than I do in order to confidently say that you think one of these things is a fault. But I can look at this and say, I know something's going on there. So in the end, this is just showing the second derivative. So maybe you can see a little bit more, feel a little bit more indicators of faults there. But I think you can agree by looking at this vintage of the seismic that there are things going on there. They're not big faults. They're not, you know, you don't see big offsets along these faults, big vertical offsets along these faults, but there's something there. And the other thing that was really nice from reprocessing the seismic is Sterling Seismic did this for us, and they did this porosity inversion that really clearly highlighted the different lithologies. So the orange is the high permeability. This is the injection zone of the Mount Simon, the orange and yellow there. And all of the blue is low permeability. So the bottom low permeability is the Precambrian basement, and the top low permeability is the Eau Claire shale seal. But the thing I want to really draw your attention to here is that when you look at, this is vertically exaggerated now, but when you look at this little topographic high here, you can see that there is this sort of greenish, light greenish unit that pops out in this porosity version. And this is inversion. And this is the unit that I was mentioning before, that's at the base of the Mount Simon. We call that informally the Argenta formation. It has much lower permeability than the reservoir and slightly higher permeability than the basement. And then The other interesting thing is that it looks like it's either missing or very thin on this basement high here. So if we zoom into that, this porosity inversion went a long way toward helping us to interpret the structure here, because you can see here, this is most likely a fault, where you can see that there's more argenta deposited here on top of this basement high. And these little green streaks in here represent these low permeability, we call them baffles within the Mount Simon, the high permeability reservoir. And we think that they had a very large influence on the migration of the CO2 plume. And I'll talk a little bit more about that later. They're discontinuous, so I'm going to want you to keep that in mind. And so this is what I'm showing here is the faults and the horizons, some of the horizons, and just the faults that were interpreted to go down into the basement. So this black line here is the top of the Precambrian basement. And you can see that there's very little vertical offset on those. If I put this porosity inversion back on there, you can still see where those faults are. But then I also put the microseismic events there, and they're not coinciding with the fault. So these are projected onto this 2D line from 20 meters away, and they're in different locations. But they do one thing that, and I showed that also in the previous slide, they do kind of focus, or most of them occur, the high density occurrences are on this basement high here. And then looking at the seismic another way, you can still see, where you can interpret faults, but this disconnect between the location of the induced seismicity and the places where we've interpreted faults. Okay, so this is just the horizons in a geologic model. I just wanted to show you the topography on top of the basement and the fact that a lot of the seismicity occurs underneath that high, and this is the right above this high is where that argenta formation is missing. And the other thing about this is that most of the induced seismicity is in the basement. 90% of it is in the basement and below the reservoir. All right, so I've talked about the faults. I showed them in 2D. Here are the faults in 3D. And I'm on this right side of the diagram, I made these three faults here intersect this large cluster of events here. So you can see that they actually do go, this one sort of bends over almost parallel to the event cluster, and then a couple other of those faults actually cut across this cluster as they were interpreted through the seismic. And I just wanted to also point out that the reason we have such difficulty interpreting the basement, faults in the basement, is because there's a low impedance contrast. You don't have layers that have enough signal difference that you can actually pull them out. So that makes it harder to get to pull out where you might see a displacement along a fault. All right, so the other important thing is the injection periods. So injection started in the CCS1 well for the first project, IBDP, in 2011. And then there was a period of non-injection of about 22 months while we were waiting to get permitting completed for injecting in the second well. And then on April 7th, 2017, injection, as I said, which is ongoing, started in the second well, the ICCS well. And here again is the map of the events. And the purpose of this slide is to show sort of the temporal relationship here. So there were more than 5,000 events detected during the CCS1 injection. So for the first injection of the first well was where most of the events happened. And they have this temporal relationship where this is the well, CCS1 well right here. And as you go through here, you can see 1, 2, 3, 4. And this histogram here represents the number of events that occurred per month. And I just put them over the month where these clusters seem to be dominating, right? And the last cluster happened here, that's number 18. And the Rose diagram here is these failure planes of 50 source mechanisms that we inverted throughout here. And you can see those are also showing not exactly the same orientations as most of these clusters. And I'll go into more detail about that later. But this is a cluster that's of interest to a lot of people. This one developed early in June and July of 2012. And that one has almost 900 events in it. And this is a depth view showing where you can see most of the events are below the basement. This surface here is the top of the basement. All right, so as you can see from this plot, on the bottom, I'm showing injection rate in blue in tons per hour, injection pressure in orange in PSI, and the downhole pressure is in gray in PSI. And there are a few little places where the injection rate and pressure goes down because we had a few relatively short shut-ins over the 3-year period. I think the longest one was about 15 days, but for the most part, the injection was trucking along at pretty much the same rate for the whole 3 years. And that's not what happens with the induced seismicity. So you can't look at those and say, well, and assume that because you have a whole bunch of events during these 2 months, that's because you had higher injection rates. That's not what we see here. And again, these orange lines here show the injection period for the CCS1 well. And I'm going to go into that in more detail and show you the same histogram right here. And now I'm showing the events that happened during the non-injection period. The events that are not during the period that's selected are sort of grayed out or dimmed out here. And so these darker green events that occur in this injection period, non-injection period, are the ones that you can see. And you can see they're dispersed pretty much throughout the whole area. So they're not migrating outward or anything. They're still continuing, settling is happening in the reservoir. But the rate of induced seismicity during the non-injection is around 10 events per month on average, right? So it's a much lower level as would be expected because no injection is happening. But then when you look at injection of the second well, with these also the darker dots here, and you can see the histogram again. I'm showing all of the events up to the summer of 2018. The induced seismicity rate doesn't increase. You would expect that once the CCS2 well comes online, the injection rate averages 1.7 times the rate of the CCS1 well. Something different should happen, but it didn't. We've got a much lower injection rate. It doesn't look like it's really getting above the rate for non-injection. So our explanation for that, I think, is in the fact that we did change the perforation interval, the injection zone. So for the first well, the injection was just above the Argenta. And then for the second well, the injection, the base of the perforation zone is about 47 meters above the top of the previous injection zone. And I'm going to show you, and you can see in these logs, the high permeability zones, and the little circles are the locations of the pressure gauges, and I just moved them over to the wells here. And so for the first well, I'm going to gray that out because for the first injection, these wells weren't active. And what I want to show you here is how the pressure, the maximum pressures for that were measured at these gauges during the injection. So here you see the lowest pressure gauge here. The maximum pressure increase was 0.8 megapascals. It's a little bit higher than that. But the other thing that was really interesting is that in this zone right here, the pressure increased much higher. And this looks like it might be because there's a significant baffle here that could have kept that pressure high below that baffle. So during the CCS1 injection, the reservoir pressure increase was higher below a baffle than it was above that baffle. And if you look at the injection for the second well the same way, and we're still monitoring in the first two wells, you can see that the pressure increased more. The injection rate was higher, the pressure increased more, but not below, right? So getting below the baffles so the way we're interpreting this is that these baffles had a very significant impact on vertical pressure migration. So it inhibited vertical pressure migration and caused the pressure to increase near the injection zones, but not so much below and above. And so I just wanted to show you a little bit about how we handled that in our geologic model, and that seemed to that we got a pretty good history match by doing it this way. So basically, we put in stochastically these baffles. We know they're discontinuous. There's these little areas, little lenses that are very thin. We can't see them in the seismic data, but they do influence the migration of the pressure plume. Now, I wanted to come back to these clusters and these 3 fractures that I showed you earlier. These clusters are colored by time. So the darkest blue is the earliest clusters that were developed. So that's where we first started to see induced seismicity, and it migrates up to red. And I stretched out the red because as I showed you earlier, most of the events occurred during CCS1. So what I'm showing is the time for CCS1 and CCS2 injection plus the interim injection. And I'm going to, in the next few slides, show you some details about these clusters. This one I'm calling G and this one is D. These clusters, the names of these clusters were based on the relocation that was done with our colleagues at NORSAR to get better resolution on the locations. So now we think we have some pretty good locations on the events. And here, I'm zoomed into cluster 3, and our NORSAR colleagues have published with us a very nice paper just recently came out in Tectonic Physics about the burst analysis. So basically what we're looking at is where temporally, if you look at 6-hour periods, you see these little bursts of induced seismicity that indicate slip on faults. And these again are colored by origin time just for this one cluster. You can see 3 different sort of bursts within this cluster that relate to the time, I show them in the histogram here, but they also have a different orientation. So if I look at that large cluster, the one that had the 3 faults crossing it, you see the same thing here. So you see these bursts of induced seismicity. They're sort of segregated in time, that I would say there are at least 2 faults here, but there are also, sorry, I didn't mean to go forward. There are also some indications of features that have an east-west strike. And so going back to this one, if we just look at sort of the general trend of the clusters, it's 50 to 55 degrees, which is not the same as the maximum stress. So we know they're not hydraulic fractures, but that's consistent with faults being reactivated. And if you take the first plane orientations of these little 6-hour clusters that develop, you also get slightly you get a different orientation than you get from the full clusters, and it's also pretty consistent with the maximum horizontal stress direction. So the point I want to make with that is that a lot of times we look at these things as full, you look at this cluster and say, well, that's showing me a fault, but it may be that in the Illinois Basin, one of the things that's driving this is that we're looking at fracture corridors. It may not actually be faults in this case. Okay, so the way we approach this for the reservoir model is to do a discrete fracture network model to add the permeability into the reservoir simulation model using the moment magnitude and measured rock properties here, and assuming a displacement based on published relationships in the literature. And then we can calculate the fracture surface area, or at least the area of the slip plane. And going back to the earthquake, comparing the natural earthquake size and the slip plane size that we've observed in Decatur, these blue and red dots here are the sizes of the events in the Decatur data set, using two different source size relationship models, and 1.2 or 1.5, depending on how you calculate the magnitude, is the largest event in the Decatur area. And that represents a slip plane of anywhere from 40 meters to 130 meters. So we're still looking at something that you might consider to be a fracture rather than a fault. And then here's the size of the largest historical earthquake within the 100 kilometers circle that I drew around the IVDP site. And this is consistent with the length of the clusters, right? So in order to get to a large sort of felt damaging earthquake, you got to be all the way up here. So this is where we are with the estimated source radii for the Decatur site. And just a little bit more about how we approach this modeling. This is one of the clusters. And this is one of my favorite things to do is the DFN modeling on the induced seismicity. You use the source mechanism failure plane stochastically to generate stochastic fractures, and then I assign them their centers to the by size to the event locations. And then we created and the reason I put that there is you look at that and you say, well, those fractures aren't connected. So this represents the size of the slip patch. So the fracture could be actually bigger. And this is what we ended up with as a fracture model for where the enhanced seismicity or where the induced seismicity and potentially the enhanced permeability would be in the reservoir, and put that into the reservoir simulation model. So going back to, again, how big are the fractures and why do we have this happening there? I wanted to bring in some work that's been done for looking at the gravity anomalies in the Illinois Basin. And so John McBride, one of the scientists we work with on this, is at Brigham Young University now, interpreted this to be, and his co-authors interpreted this to be sort of a bowl-shaped intrusion. He thinks it's a sill. This is likely, or could be that, representing that area here. But the main point I want to make here is that you see this big, strong seismic reflector here, and maybe there's this little thing here that you can interpret as a fault, but it also doesn't have big offset, right? And so it could be that these things are influencing the igneous rocks above that. And then when you look at the this semblance slice through the seismic data, you can see that there are some trends here that may be controlling where we're getting this induced seismicity. And the last thing I want to do is compare to wastewater injection and look at places where we have similar injection rates. So if you look at the Decatur wells, over 3 years of injection, the injection rates are comparable, at least for the second well, to some of the injection rates in the East Texas Basin, where you get felt seismicity after 1 year of injection. And in Arkansas, you get felt seismicity after 1 year of injection of water, wastewater, and we're doing about 2,000 cubic meters per day in all of those cases. But in the Williston Basin, which may be more similar to the IBDP than these other basins, they have much higher injection rates, and you get some induced seismicity, but it's also not felt seismicity there. So the structure has something to do with it, but I'd also like to argue that the chemistry and the thermal, the PVT relationships of supercritical CO2 also influence that, because for one thing, reservoir pressure will increase linearly with H2O when you inject water, but supercritical CO2 is compressible. So maybe that's making a difference in terms of what we're seeing there, because to date, there haven't been any felt seismic events in any of the CO2 injection projects that have been done across the world. So finally, I just want to say, sort of summarize what we think we've learned from analyzing the data in this project. One, the same thing that we see with wastewater injection is that the induced seismicity occurred primarily in the basement. So the rocks there were subject to slip, but after changing the injection depth to less than 50 meters shallower. We're still pretty close to the basement. We have very little induced seismicity. So there are other things going on here that are controlling whether or not you're going to get induced seismicity in this location. We had a challenging fault characterization because there were small vertical displacement faults. And we think that the reservoir heterogeneity had a really significant impact on the behavior of the reservoir. The table that I showed that I just want to raise the point that maybe there are other factors that should be considered when you're comparing induced seismicity from CO2 to induced seismicity from wastewater injection. Like one obvious one is the CO2 is buoyant and the brine is not, and the injection of the CO2 at Decatur probably went down because the baffles wouldn't allow it to go up as much as it wanted to. So we know that more work is needed to understand the potential reservoir response. Every reservoir is going to be different geologic settings, et cetera. And we still feel like the Illinois Basin is a great place to look at this and potentially store CO2. Thank you. Oh, first, I just want to thank our sponsors. This project was funded by the Department of Energy, and we have lots of work going on with collaboration with the Midwest Regional Carbon Initiative and petroleum experts in Schlumberger for software donations. Thank you very much.
That's great. Thanks, Sherilyn. A really great overview of a lot of fantastic work there. So on the chat, there's a number of kind of detailed questions, but before we get into the details, I thought maybe I'd ask kind of a higher level question. There's a lot of interest, obviously, in other CO2 injection sites and a lot of questions on risking the sites for induced seismicity. So based on all the great characterization work done in Illinois on the Decatur project and all the learnings from the injection itself and the monitoring, in terms of kind of a look back of characterizing the seismic risk in the area, I think you touched on this a few times, but do you think we've moved the ball? We've have better insights to allow us then to try to do better seismic risking for other potential sites?
I do. I mean, I think there were so many different factors controlling where we got the induced seismicity in this site, and they were a lot more subtle than you expect. And I think that it just says, it shows that what you need to do is integrate all the geology, right? Which I'm sure that's what people are doing, but the things that are going to control it are not just how close you are to the basement. What's controlling it is your geology and your reservoir, and what kind of connection you have to the basement, or whether you have something else that's forcing, which I think happened here, the CO2 to go into the basement. So that topographic high there didn't have the bottom seal, and it's also highly fractured because we have image logs and core through there, and it's very highly fractured. So it's just like it was going to go there if it was forced down.
Great, thanks for that. So maybe just going through some of the detailed questions on chat, and I'm going to apologize to the name of the first person that I'm sure I'm not going to pronounce correctly, but Shivajit Bhattacharya is asking if you have any information on the porosity range in the Mount Simon from the inversion work. So what range of porosity we're looking at?
Yeah, sorry, I didn't mention what the porosity was. The Mount Simon average porosity, I believe, is 22%. And it can get as high as, it's 22%. It can get in some places as high as 27%, but it's, the injection zones were ranging around 20%. And the Argenta below that is 8 to 10% porosity.
And what's the initial pressure regime, Sherilyn? Is it under pressure?
No, it's normally pressured.
Okay. So Kevin McCormack is asking a question, how much micro earthquakes were in the area prior to injection. Do you have any baseline monitoring prior to the start of injection to get a hand on the background activity
Yes.
rate?
Yes, it was monitored for 18 months prior to injection. I believe there were 8 earthquakes or 8 events identified that were interpreted to be micro earthquakes. They were all below, I believe, magnitude 1. They were below magnitude 1. I can't remember how much below magnitude 1. They were all, sorry, -1, below magnitude -1. There were a lot of events because there's a lot of industrial stuff. So they had to, they only ended up with 8 things that they could locate during that 18 months.
Great. Then moving on, Yunyu Alida Lee is asking, is there measurement of pressure change as a function of time with injection rate? You mentioned those pressure monitoring gauges, but how is it changing with time?
Yeah, so
the
pressure is measured at a really high frequency. So the pressure change, we only had, so you could do pressure change as a function of time. I didn't show that. All I showed was the highest pressure increase at those locations. But yeah, you could, I didn't show anything about measuring pressure with change with time though. I will say that the plume, the CO2 plume was very small. The pressure change, it didn't take very long for pressure to get from the CCS1 well to, or the CCS2 well to the CCS1 well, but it depended on the azimuth. It would get, the pressure would migrate faster in the northeast direction than it did northwest, obviously, because it was going against the grain.
Presumably those pressure monitoring measurements were helpful for history matching of the reservoir simulator that you alluded to.
We definitely relied on those, and that the whole idea was to try to match those, and we're still working on getting that published because we have some of it was more most of the we're able to, our simulation reservoir simulation engineers were able to match most of the pressure gauges for the history match, and it was only after the baffle and fracture network modeling that they were able to get a good history match. And we also played around a bit with trying to make the faults have different permeability properties, and that didn't seem to change much.
Okay, great. There's another question from Shivajit, and I'll generalize it a little bit. Prior to injection, how much injectivity study was done on the injection well? Was there spinner logs and step rate tests?
Yes, there were spinner logs, and the spinner logs were done periodically, and that was also used to inform the reservoir simulation model.
All right, and then Han Kao is asking, who made the decision to inject at a shallower depth? You mentioned that baffle, but was that a mitigation strategy as part of the second phase of the injection?
I would say yes. It was a conscious decision to try a slightly higher injection. Still, the injection, the goal was to inject into the high permeability zone there, and there was another zone that was slightly higher, but it was a conscious decision. I don't know if at the time it was mitigation because this induced seismicity was pretty small, right? But to avoid it, you don't want to get it worse. There was a conscious decision to go a little shallower. So yes, we learned took that from what we learned from the first well and applied it to the second well.
Excellent. Umesh Prasad's asking if there's a decrease in strength or impedance in the rock mass between the two injection as a function of time. So maybe more generally, you mentioned time lapse seismic, where you able to image the plume with time?
There is a plume image. So I'd have to say yes. So yeah. Schlumberger did the processing, and that was done on the first vintage of seismic. But we do have a 4D seismic image from that has a plume image extent identified in there. Yes.
Great. And then Jorge Berrios is asking if there's a three-dimensional mechanical earth model for the area.
Yes. That's another thing that we're working on trying to get published. We do have a 3D mechanical earth model for the area.
Great. And then Jens asks an interesting question. So based on the success of the injections so far, has there been thought or any modeling work to look at scalability? So could the number of disposal wells be increased in the area? And maybe tie that back to my initial question on seismic risk. Is that increasing the injection rate, has that been looked at in terms of trying to predict what the seismic response might be?
That would be the purpose and goal of our Illinois Storage Corridor project. So we are looking at scaling. I didn't show that slide. But I have a slide that shows scaling from IBDP to ICCS all the way up to 50 million tons, you know, within the Illinois Storage Corridor project. So the answer to that is yes. We are working on that now.
Great. And then another question on chat here from Andreas Cheveria. He's curious if there's any temperature measurements with the pressure, and if that's giving any insights to the pressure plume.
There are temperature measurements, but I don't know a lot about it, and so I can't answer that question. I would say the reservoir simulation engineers we worked with, we didn't use the temperature measurements, but they are there, and so the answer to the question of whether it would give us any insights is I don't know. We didn't use it. It will be available soon, though, for other people to use.
He's also asking more generally about fiber optic data, but I'll maybe extend the question. I remember there was a fiber optic cable being installed for passive monitoring. Was that ever successful to pick up any activity?
Yeah, my understanding is that was not successful. That was a Lawrence Berkeley Labs project, I think, and so I don't think there were some issues with it, and it was not successful.
I have a question.
Go ahead.
Marty.
So you mentioned in CCS2, the injection interval is shallower than CCS1. So is there any concern about compromising the caprock? How far is that to the caprock? And probably if you pressurize too much in long term, you may compromise caprock if it's not as thick as you think.
Well, that's why we monitored, right? So you want to make sure that the induced seismicity doesn't start occurring shallow. The Mount Simon Reservoir is 500 meters thick right here. The first injection was at the bottom of it. The second injection was 47 meters shallower. It's still close to the bottom of it. The Eau Claire Shale is also quite thick in this area. None of the induced seismicity got close to the base of the Eau Claire Shale.
Okay. So, but maybe other modes of failure may happen that you don't see in seismic monitoring. What do you think?
Well, I think that's possible, but I'm not. I think the only way to, if you can't see it in seismic monitoring, I guess you'd have to look at it in terms of where you think the fluid pressure goes. But yeah, we didn't do that, so.
Yeah, so I've seen in some CCS projects that they monitor carbon dioxide concentration on the ground surface. So that can be something to just verify if there is any of leakage to the surface.
Yeah, well, we did monitor on the surface. Nothing, there was, I didn't show, I was just talking about the deep monitoring in this talk, in this presentation, but there was significant monitoring on the surface. Nothing was detected.
Okay, thank you.
So a couple more questions, Sherilyn, have come in. So we'll maybe go through them and then we can wrap this up. So Ivan Wong's asking the more distant clusters from the injection. Does that give any insights in terms of pressure migration away from the injection well?
Yeah, because the pressure, it must be, I don't know. So, okay, so here's the thing. The burst analysis, the reason we did the burst analysis was, or my co-author, Ana Maria Dichiarante, did the burst analysis. One of the questions she wanted to answer was, can we make a case that it was pressure, or could you say that it was stress transfer? And she was not able to identify any patterns that would support that. So at this point, I don't know what I can say about pressure migration that far away, right? It probably is that far away because it happened over time. The CO2 is increasing the pressure, compressively, and then the water, it would be, the brine would be increasing, and the pressure increase away from the well should also increase eventually. And so it doesn't take much to cause appropriately oriented faults to slip. And so I think it could have been pressure. We just don't have a way to confirm it yet.
I would think it'd probably be a good thing if pressure is able to migrate that far, right? Because that means it can't build up to a large degree locally near the wells. You might have a bigger reservoir, is that right?
Say that again.
If the pressure is able to migrate larger distances easily, that would suggest that the reservoir that you're dealing with is probably more interconnected, and you probably have a bigger reservoir, and your pore pressure near the well might not get as high. Is that kind of what you're thinking?
Yeah, that's what I'm thinking, because it's a very permeable reservoir, right? So high porosity, high permeability.
Okay, one here, Sherilyn, then we'll kind of wrap up. Jorge is asking if there's any differences in the horizontal stresses between the two injection wells.
Not really. They both have the same orientation, same kind of lithology. They're fairly close together. They're less than a mile apart. So they're very similar.
Great. Well, Sherilyn, on behalf of ARMA and the Induced Seismicity Committee, we'd like to thank you for the excellent webinar. A lot of interest in this topic, and it's great to see such a thorough, comprehensive piece of work. Ahmad, did you have any closing remarks you wanted to make?
No, thanks again, and we're looking forward to our continued service to the community by providing these webinar series. And so I would like to encourage everybody to attend and join ARMA if they're not members.
Thank you for having me.
Thank you.
Thank you so much,
Absolutely.
Sherilyn.
Just a quick reminder to everyone, the next webinar will be December 3rd, Serge Shapiro. We'll be talking on the seismogenic potential modeling work that he pioneered. So another interesting topic. And thanks again, Sherilyn.
Thank you. You're welcome. Bye-bye.
Thank you. Bye.
Bye.
So
We're done, right? Stop recording.
I stop